Okay, so we're going to introduce implicit differentiation here. And at first you might be saying, I don't even know what that means. What does it mean to have an implicit function? And so the idea is that for most functions, we just plug in a value. We say, okay, take x and you're squaring it and you're multiplying by 5 and you're adding 7 or whatever. But for implicit, you might not have y equals some function of x. So for example, you could have the function x squared plus y squared equals 25. And even right there, I said the function, but this isn't a function, right?
Right, it's not a function. And you may be tempted to say like, well, I can solve for y, but in that particular case, you get a plus and a minus. And as you can just see what was drawn there, that doesn't look like a function to me. It doesn't pass the vertical line test.
Yeah, so if you tried to solve it to make it more friendly, I guess, yeah, you would get two different parts. And so you could think about it as two different functions, and that might work. Although this would be really unpleasant to have to take the derivative of. I mean, you can do it using the chain rule, but it's unpleasant. And the problem is that there are times that won't be possible, right? So for example, what if you had a function and it looked like sine of x times x to the 5th minus cosine of y squared times x times e to the y equals 1. No. I don't know, like something crazy, right? You can't solve for y in this in that, again, not a function, in that curve. We keep saying curve, in that curve. Okay, so this is what we call a curve that's defined implicitly, because you have x, which is still an independent variable, and then you also have y, which we can think of as a function of x, sort of dependent on x. But you can't just solve y equals something of x, right? So the way that we're going to do this is we're going to remember, in this case, that y depends on x. So think about it here that I can plug in anything I want for x, but whatever I plug in for x, y is going to be fixed. It won't just be one value. In this case, I might get out two possible values, but y will be depending on x. And so if I think about using the chain rule, and I want to take the derivative of y, right? If I try to take the derivative of x, for example, d dx of x, I'll get 1. But if I try to take the derivative d dx, so with respect to x, of y, I'll get y prime, or dy dx, right? Because again, y is dependent on x. Okay, so let's go through this. So let's think about taking the derivative of, again, with respect to x, of y squared, x squared plus y squared on the left side and on the right side. Okay, so this is from my original curve. So if I take the derivative of x squared with respect to x, what will I get?
Well, that's just like a normal derivative, so I should get 2x using the power rule.
Exactly. And again, using the fact that when we take derivatives, we have a sum rule. We can take the derivatives separately. Okay, and then this is the part that's different, because when I take the derivative with respect to x of y squared, I can do almost the same thing. I can do 2y, but then I'm remembering that y is dependent on x. So I have to think about also including y prime, right? So think about, actually, let me do a little side note here.
So that's kind of like the chain rule.
Right. If I had like x squared plus 7 to the 5th, and I took the derivative, right, by the chain rule, I get 5 times x squared plus 7. And then I would have to take the derivative of what's inside that. And so x squared plus 7, the derivative would be 2x. So it's the same thing here, right? I'm taking
Don't forget the
derivative of,
power.
oh, thank you.
We all do this. The power on x squared plus 7.
That's why there's two of us.
Yes, exactly.
So I'm taking the derivative of y squared here, and that's, bring the 2 down, change the exponent, now it's 1. But then I'm multiplying by the derivative of what's inside. If I don't know what that is, it's just y prime, right? And then on the right side here, the derivative of 25, that's a constant, so that's not changing, so that will be 0. And now to solve, if I was asked for y prime, now I can solve for y prime, right? I move over the 2x and I divide by 2y. And this is something that might be different from what you've seen before, because now the derivative y prime is dependent on both x and y. So if I wanted to find it at a particular point, right? So if I wanted to find it at some point, let's say here, this would be the value 0,
5.
5, yeah. Circle with radius 5, thank you. I would need to plug in 0 for x, and I would plug in 5 for y, because I need to specify whether I'm looking at this point or whether I'm looking at a different point that also has x equals 0, right? And as we can see here, y prime at this point 0, 5 will be 0, which matches up with our picture. Okay.